Hello everyone, welcome again. So today we'll be talking about the energy module of the Year 11 chemistry syllabus. And so we've been talking about reactions and energy and how they kind of relate to one another. And in today's lesson we'll be talking more about reactions and bonds. Okay? So here you have hydrogen and oxygen sort of coming together, striking one another, and then you get water, and you get an emission of energy as well. So that's what a hydrogen flame is all about. You're just burning hydrogen, getting water out. Okay, so that's the kind of thing that we'll be looking at today. So the first thing to note is what bond energy is. Okay, so bond energy is the amount of energy required to break up 1 mole of molecules into their component atoms. Okay, so remembering a mole is just simply a number, it's just a number of molecules, so it doesn't matter what the number is right now. But what we're doing is the bond energy is, if I was to have that number of molecules, how much energy would it take to break up each of them into just their atoms? So now there's 2. Okay, so that's what bond energy is. So if you think about it, it's a measure of how strong these bonds are, because the more energy you need to put in for the same amount of molecules or atoms or whatever these things are, then if you have to put more energy in, the bonds must be stronger because they don't want to break as easily. Okay, so that's why they're a measure of this bond strength. And it depends on the atoms involved in the bonds as well as the number of bonds in that molecule. Okay, so it depends on what the atoms are. That will tell you different things about the bond energy. And also the number of bonds will change how much bond energy these things have. Okay, so molecules with large bond energy will require more energy to break apart, obviously. Okay, we went through that sort of. So here's the reason why. Okay, so let's have a look. Bond energies for common bonds. Okay, so C to C bond. So just if we had something like this, 2 carbons bonded together with a single bond, that would take 346 kilojoules per mole. Okay, fairly average number. Now the oxygen double bond. So remembering that oxygen is this, and so it has 2 bonds. So this is 494 kilojoules per mole. Okay, fairly, again, quite a not too high number. That's not too bad. And then you've got the carbon triple bond. Okay, so you may not have ever heard of a triple bond before, but they do exist, let me assure you. And that equals 835 kilojoules, so more than double the carbon to carbon bond. Okay, so what do you notice? The one thing that you should notice is that as you increase the number of bonds, the bond energy increases. The amount of energy needed to break those up goes up, which makes sense, right? So if you were to have like a string wrapped around something, 1 string will break more easily than 3 strings. Yeah. So now, now the next obvious question is, well, if I have a double bond there compared to a single bond, don't I have? Let's just talk about carbon now. So each dot represents an electron. So if I have a double bond, that means I have 4 electrons really, really close to each other, right? And so if they're really close to each other, shouldn't they be repelling each other? And shouldn't that bond be very weak then? That is partially true. Yes, you've got lots of electrons close together. But what you have is, if you look over here. So here's a single bond. There's 2 electrons in the single bond. And so these 2 electrons attract the positively charged nuclei, right? Now you put more electrons here, and what happens is that they actually attract them more greatly because there's more charge here. There's more electrons, meaning that it attracts more strongly. So they actually get closer together. So that's why the bond energy actually increases, because it can actually pull these nuclei closer together, which increases the amount of energy you need to separate them. Okay, and that's why we get an increase as we increase the amount of electrons, even though it seems like they should just repel each other and destroy that bond. So yeah, it can be seen that the high numbers of bonds produces greater bond energy, which again sort of makes sense. Now, bond breaking and reformation. So we kind of covered this before, but the energy released or absorbed by a reaction is related to the bond breaking and reforming. Okay, so when you have bonds breaking, it absorbs energy. When you have bonds forming, it releases energy, and that's in that picture there. So bonds breaking takes up energy, bonds combining or forming gives you energy. So again, energy is required to break bonds. And when bonds are formed, energy is released. Okay, so we're just going to keep drilling that into you because that's the key point of this. So if more bonds are broken than reformed, the process is endothermic. Okay, so what does that mean? So if you break way more bonds than you form, it means that you've taken up more energy than you've actually given back. So that means that the process, in terms of its net amount of energy, it needed more energy than it could give. So it's endothermic, so it's absorbing energy. So this is because more energy is taken in by the bonds than released in the formation of new bonds. So the process is endothermic if the bonding energy of the products, so this is another way of thinking about it. So if the bonding energy of the products is lower than the bonding energy of the reactants, it's also endothermic. So the bonding energy of the products, if it's lower, it won't take as much energy. They're more unstable. So if it's lower than the bonding energy of the reactants, then we needed to take in a lot of energy to break up all those very strong bonds in the reactants. Okay, so here's a quick diagram. So in an exothermic process, heat energy is given off. So the heat content of the system has decreased, so delta H is negative. But yeah, endothermic process, heat is released. So exothermic process, heat is released. Endothermic process, heat comes in. So more energy was taking in, breaking the bonds, okay? If we're talking about endothermic processes. So of course the opposite happens for exothermic reactions. The bonding energy will be higher in the products than in the reactants, and energy will be given out by the system. So what that means, that the bonds broken are fewer than the bonds formed. So that gives you the opportunity to make lots of new bonds, which means there's lots of energy release, and that gives you energy out that you can feel. Okay, so that wraps up today's lesson on bond breaking and reformation. So we looked at how bond energy relates to these different chemicals, and so now we'll go on to the question segment, and hopefully you'll learn something new about bond energy because there are quite some challenging questions here. Okay, so the dissolution of salt in water is an exothermic process. Explain why heat is released in this process with respect to bond formation and breaking. Okay. So the bonds between the ions in NaCl are broken. So that's what happens when we dissolve them. We put them in water, the water pulls them apart. Now this requires some energy, and that energy is in the sort of thermal, is actually part of the temperature of the water. So there's energy in the water. However, new bonds are formed when the free ions bond with the water molecule. So now that they're separated from each other, water molecules kind of surround them. And that's what dissolution is, when water pulls something apart and then surrounds the components. The energy released by the formation of new bonds is greater than the energy required to break the original bonds, thus releasing energy. Okay? So that's why this is an exothermic process. When you break up the bonds in the ionic salt, then the water surrounds them. Those new bonds formed by the water surrounding those ions releases energy, and that gives you an exothermic process. Question 10. The energy needed to break bonds can be procured in many ways. List the major sources of energy for chemical reactions. Okay, so what are the ways we can get energy for the chemical reactions? So the first one we've talked about ad nauseum, and that would be heat. Okay, we talked about heat a lot. So that's a general one. We could get it from electromagnetic radiation or light. So original photographic film, so not digital. So we're talking about film cameras. The early ones, the ultraviolet light and the light from that we could see basically struck some crystals of silver nitrate, forming solid silver. So that reaction actually happens because of light. And there are many other reactions that happen because of light. So think about photosynthesis. That's another reaction where light is sort of the energy source. And another typical one is electricity. So when we separate water into hydrogen and oxygen, we use electricity. But sort of more practically, when we want to separate metals from their kind of impurities, we tend to use electricity as well. Okay. So moving on to question 11. Okay. The N2 molecule does not often participate in reactions unless they are at very, very high temperatures. Okay. Explain why N2 is much less reactive than the O2 molecule. Okay. So we have to think about, why is N2 so much less reactive, even though it's N and 2 and oxygen is just O and 2? So firstly, we need to understand that nitrogen has a very strong triple bond. Okay, so it has N triple bond N. Okay, and the total bond energy is 942 kilojoules per mole. The oxygen bond energy is only 494. So the N2 is almost twice as strong as the O2 in terms of its bond energy. So from that bond energy data, compared to O2, a large amount of energy needs to be inputted to break the bonds between the nitrogen atoms. So we have to put in heaps of energy just to snap those 3 bonds and get nitrogen to be free. Now oxygen requires almost half of that just to do the same thing. So therefore the N2 molecules rarely participate unless there is an abundance of energy, and that's the high temperatures that I spoke about in the question. Now for oxygen, because the bond energy is so low, it doesn't need as much energy, so it can participate in many reactions because it doesn't need as much energy to be available for it to break up. Okay, so that makes sense. We'll move on to the last question. So here we have carbon dioxide, CO2, is often a product of combustion reactions. So when we burn things, we get carbon dioxide out, and that's what we're afraid of in terms of global warming. Some people claim that a solution to this problem is to turn that CO2 into methanol. Okay? Methanol is a fuel. It's used in race cars, so Formula 1, those kind of things, all methanol, so not petrol. So here's your methanol reaction, and it's reacted with hydrogen gas. Okay, so the CO2 plus hydrogen gas gives you methanol and water. And the H2 is extracted by splitting water, normal water like this, into O2 and H2. Now given that the bond energy for CO, so the bond energy between the C and the oxygen, the double bond, is almost 800 kilojoules, and the bond between the hydrogen and the oxygen in water is 456, explain why this plan may not be feasible at this point in time. So the bonding energy of this C double bond O is very high. Okay, that's the first thing. This means in order to break the bonds, a lot of energy needs to be expended. Okay, you need to use a lot of energy to break them up. And the bonding energy of H to O is also quite high. So in order to produce H2 for the reaction, large amounts of energy also are needed. Okay, so you need, it's a two-pronged thing. You need a lot of energy to break up the C and O, and you need a lot of energy to break up the H and O. Okay, so now we've got a bit of a problem. Therefore, methanol production, this particular methanol production, requires a large amount of energy, which makes it not feasible for large-scale production at this time. So because there's so much energy involved, we may not be able to use this to solve our global warming problem. And how we fix this would simply be to find better catalysts and reduce the amount of energy that we need to actually deal with this particular problem. So that wraps up today's lesson on bond energy. So we talked a lot about what bond energy is and how it varies between different chemicals. And we looked at what it means and how it relates to chemical reactions. Okay? So in the next lesson, we'll be talking about your first-hand investigations regarding exo and endothermic reactions. And so I look forward to seeing you at our next lesson.